So let's begin with the small recap of what we have done earlier in the previous class. So in the previous class, we have introduced the concepts of EMF generation in single phase, two phase, and three phase, and how these values can be represented in a waveform as well as in the phasor diagram. Okay. So the last topic which we were dealing was the three-phase system, and in the three-phase system the phases are separated by 120 degrees as shown in the figure. Okay, so this is the phasor diagram, and it can be, if it is assumed that it is a symmetrical system, and since it is a symmetrical system, so the phase value of the EMF of each phase is same. Okay, so if there are three phases, A, B, C phase, and their magnitudes are same, and they are produced due to the conductors which are placed in the magnetic field, and these conductors terminals are A1, A2, B1, B2, and C1, C2. So if we assume the x-axis as a reference axis and place the EMF produced due to the first conductor A1, A2 here, then the second phase EMF, that is EB1, B2, it will follow the anti-clockwise direction and reach the x-axis after the passage of 120 degrees. Okay, or you can say that it is lagging the A phase by 120 degrees. Okay, so we can represent the this by using the vector algebra representation as shown as EP minus 120 degrees. Okay, so similarly, using de Moivre's theorem also, you have studied earlier that if a complex number is represented as E is equal to I theta, then it means, sorry, this is like this, E is equal to I theta, then it means that this magnitude is, if this is the magnitude, and the vector components in the x-axis and the y-axis can be represented in the polar form using the trigonometric components. So it becomes EP bracket starts cos theta plus I sin theta. So we have used the same here and represented this EMF as EP cos of minus 120, and also minus sign is there, huh? Cos of minus 120 plus sine of minus sine of minus sine minus 120 degrees. Okay, similarly this C phase, this is lagging the A phase by 240 degrees, Okay, so we can say that this is lagging by 240 degrees because it will reach the reference axis or the x-axis after the passage of 240 degrees. Or we can say that it is ahead of x-axis by 120 degrees. So since we know that in a sinusoidal quantity, the angle which the sinusoidal quantity is having, or the value of the sinusoidal quantity at any particular angle, will remain same if we either add 360 degrees or we subtract 360 degrees. Okay, so because sinusoidal waves repeats itself after every 360 degrees or 2 pi radians. Okay, so minus 240 plus 360 is 120 positive. So it can be represented in such a manner also, that EP 120 degrees, or you can say EP angle 120, J 120. So that becomes EP cos of 120 plus I sine 120, and it is represented like this. Okay, so if we use the uh, instantaneous EMF concept, then these instantaneous EMF resultant will be like this. So it is represented at EM sin omega t minus 120 and sin omega t minus 240. So it becomes zero. How come it becomes zero? Because these two phases are separated by 120 degrees, and this minus x-axis or the resultant is the angle bisector. So it is making the angle of 60 degrees. So cos of 60 degree is half. So half component is contributed by C phase, half contributed by B phase, and so this is minus 1. If you assume that the magnitude of the maximum EMF is 1, so it is minus 1 in LHS and plus 1 in RHS. So when we add these two, it becomes 0. Okay, so phase sequence I have explained you earlier. It is the sequence in which the different phases are crossing the reference axis. Okay, so this is the A axis, B axis, and C axis. So the phase sequence will be ABC, and if C is here and B is there, then it becomes ACB. So focus on this. This is the star connection system. Okay, supply system of star connection, and it is also known as Y connected system, as we have discussed in the unit 1 also. So this is the circuit, this is the connection diagram, and next part is its phasor diagram. So we will understand both of these things one by one. So these three phases are connected by neutral wire as shown. So, and we are assuming that the magnitude of the phase voltage is same. So symmetric system is there. So these are same. Next is our line voltage. So what is this line voltage and phase voltage? First of all, phase voltage is the voltage between any line and the neutral. Okay. So if we are calculating the voltage with respect to neutral, for example, this is R phase and neutral, this is having the EMF of ER. Similarly, EY and EB. Okay. So, and next is the line voltage. Line voltage is the voltage between any two outers or phases. Okay. So, these are three line voltages ERY, EBR, and EYB. Okay. So, we are required to calculate the relationship between the phase voltage and line voltage, phase current and line current, and we will take the help of this phasor diagram. Okay. So what is happening in this phasor diagram? Let's focus on this and how we are required to draw this phasor diagram. So we are taking RYB as a phase sequence. So what we are to do, we are required to first of all draw R phase, Y phase, and B phase 120 degrees apart. Okay, and label them accordingly. Okay, ER, EY, and EB. Okay, so these line voltages are so these are three phase voltages, but the line voltages are also drawn on the circuit diagram as well. So what is the line voltage ERY? As I have just mentioned, it is the voltage between the two phases. So when we talk of the voltage between the two phases, it means that we are taking its potential difference. Okay. So it is represented as, say, ERY we are talking. So it is represented as ER minus EY. Okay. But when we talk of the vector representation, there is a law called parallelogram of vector addition. Okay. So this is represented as addition like this, that ER vector plus minus of EY vector. Okay. So how this is helpful? It is helpful in determining the line voltage. Okay. So ER minus EY. So EY is with this, with us. So if we draw a line which is equal to EY and at 180 degrees difference, so it becomes minus EY. Okay, so now the things become easy. Okay, now what we have to do, we have to calculate the this difference or calculate the obey the parallelogram of the vector addition. So this is the ER, EY. So we have to draw a line which is parallel to ER, okay, and equal to ER. Okay. So this is ER and this is minus EY. So we will connect minus EY with this, and this is the resultant ERY. Okay. So what we can interpret from here, that this resultant ERY is the line voltage and it is having the angle 30 degrees from each of the phases. Okay, again let's revise. This is 120 degrees. So when it is reversed, this one of the phasor is reversed, then the angle between the phasors becomes 60 degree, and when the its bisector is taken or parallel comma factorial addition is applied, then it becomes the angle between the line voltage and the phase voltage becomes 30 degrees. Okay. Okay. So as we have calculated this ERY, similarly we can calculate other two line voltages EYB and EBR. Okay, this is our EYB. How it is calculated? EY minus EB. EY is already known to us. EB is here, so we will take its negative vector and then apply the vector law of addition. Similarly, this is EBR, which is the line voltage of the third component. Okay. So now we will calculate the magnitude of line voltage in terms of phase voltage. Okay. So what we are going to do, we will use same formula of vector addition, which is a square plus b square plus 2ab cos of angle between them. Okay. So same is applied here, er square plus ey square plus 2er and so on. So what else or what more you can do uh, in this diagram to be more precise, that when you are calculating this you are required to put mod here, arrow here, and then square here to become mathematically correct. Okay. And you know that the angle between the er and minus ey is cos is 60 degrees. So when we apply cos 60 degree, it becomes half. And since this symmetrical system, so the magnitude of all these phases are same, so it is replaced by ep or phase voltage. So these are replaced, so this two cancel out with this two. So what we get, that line voltage is equal to root 3 times phase voltage. Okay. And in the this star connection, current remains same. Line current is equal to phase current. This is one of the property of the star system. So now we will calculate the instantaneous power in case this load is connected or the balanced load is connected to the supply system. Formula remains same as we have discussed in the single phase system, that in the single phase system, since there was one single phase, so we have calculated the instantaneous power as the multiplication of instantaneous voltage and instantaneous current. Okay. So since here there are three phases, so we are required to do same thing three times for different phases, or er ir plus ey iy eb ib corresponding to these three phases. Okay. So what was the instantaneous value of the voltage or emf in the single phase? It was em sin omega t. Okay. So but here we have used this ep. What is this ep? This is the phase voltage, and since it is represented in capital letters And as I have explained you earlier as well, then that the capital letters means that we are talking of RMS values. Okay, so in the single phase system, we come across this formula Em sin omega t or Vm sin omega t. So to make this RMS value as maximum value, what we will do, we will multiply it by root 2, because we know that the RMS value is equal to Em by root 2. Okay, and same this component is substituted for Em in this phase. Okay, so this is the ER or the phase R phase EMF when we are talking of instantaneous values. Okay, so since these three phases differ each other by 120 degrees, so but the magnitude remains same. Okay, so this is the magnitude, maximum value or the amplitude, it remains same, only difference will be the phase difference. So Ey is equal to root 2 EP sine omega t minus 120. Similarly, it becomes minus 240 degrees or plus 120 degrees. It is all the same. Okay. Now we are discussing the case that this supply system is connected to a three-phase load. Okay. So when there is a three-phase load, and as I have told you earlier as well, that the maximum load which is present or used worldwide is resistive load and inductive load. And also it is well known fact that the pure resistive load and pure inductive load are not easily found. So we can say that the pure resistive load always have some inductive components, and similarly all inductive load always have some resistive components. Okay, so it is realistic to assume that the loads are RL load. Okay, so again we are calculating or deriving this power equation using the assumption that it is the RL load, although we can derive using each load, whether it is R, pure L, C, RL, RC, RLC, whatever it may be. Okay, but since most relevant is RL load, so we are going for that. So in the RL load, what we know that the phase current lags the phase voltage by say any phi angle. Okay, so this is the phase voltage or EMF. This is phase current. So earlier it was in the single phase what we have studied. One is Em sin omega t, other is Im sin omega t minus phi. Same is here. So this is Im sin omega t minus phi. This is the phase value which is RMS. So we have multiplied by root 2. Okay. Similarly, this is the equations for Y phase and B phase current. Okay. So since we are now aware of all these instantaneous voltages and currents. So we will substitute these values in this instantaneous power equation. Okay. So when we substitute these values here and do some mathematical calculation, some of the factors does cancel out each other, and the resultant value which we get is this 3 EPIP cos phi. It is similar to what we have derived in single phase. In single phase, we have derived VI cos phi. It was applicable to resistive, inductive, capacitive, RL, RC, each load it was applicable. Just the value of phi was required to be substituted. Okay, so same is this condition here. Here also it was voltage, RMS voltage of the phase. Here also it is same. Second, it was the RMS current, which was phase current. Here also it is the same. Same angle cos phi is applicable here also. But only difference is that since it was a single phase, so you can say 1 is multiplied by VI cos phi, and here since it is a 3 phase, so the multiplication is by 3. Rest everything remains same. You can expand this instantaneous power, okay, and check out yourself which are the values which become, which cancels out each other, and also there is possibility that we may get some of the sinusoidal components as well. Okay, but if we are getting the sinusoidal components and the value of the average power over the whole cycle, or average value for the any sinusoidal quantity for the full cycle becomes 0, so that factor is also to be taken as 0. Okay, so now we can represent this in a different manner as well, using line voltage. So this is the representation using the phase voltage. So Ip is equal to IL, so we can substitute Ip is equal to IL, and EL line voltage we have just derived, that is equal to root 3 EP. So the value also becomes like this, root 3 EL IL cos phi. Okay, where cos phi is the power factor. So if we are uh, we want to calculate the other powers, we can also use using the power triangle. So in the power triangle we note that this is the apparent power, okay, and this is our average power or real power. So real power is calculated as 3 EP IP cos phi. So it means that since this is the cos component of the right angle triangle, so this apparent power becomes 3 EPIP. Similarly, this reactive power becomes 3 IP EP sin phi. Okay, clear? So in the balanced system, the potential of the neutral or the star point is 0.